Hi there, welcome to 4b.3. This is where we're going to start to look at how we use exponential functions. And so we will talk about some of the transformations that we've had in the past. And we'll look at two different types of exponential functions. One where it doesn't really have a horizontal asymptote change. So the horizontal asymptote is 0, there's no vertical shift. And then one where if you're given an equation, the vertical asymptote would change. And so there's two real learning targets here. And the first one is you have to create the first one is you're given an equation, you have to kind of interpret what the equation is telling you. And the second one is you have to create the equation yourself. And so both, these are both different skills in themselves. Not one more difficult than the other. They're just really different. But to get to that, we want to start talking about percentage change, because a lot of these applications are going to deal with percentage change, and so we want to make sure that we're comfortable dealing with percentages. So the question is a very straightforward question. If you're to lose 20% of your money, what percentage of your original money do you have left? And if your money was to grow by 15%, what percentage of your original money would you have? B is a little bit trickier, but both of them will help us understand what the base is that we're going to use. And that's the question. The next question is asking, what numbers would you multiply by continually to find out how much money you have left? There's two ways to do tax. Tax is 13% here, and so if we buy something for $20, we can multiply that 20 by 13% and add back the 20, or we can multiply by 1.13. And I want to see why we do that. And so if you lose 20% of your money, you have left with you 80%. And if your money is to grow by 15%, what percentage of your original money do you have? And that's 115%. Numbers you multiply by are 0.8 and 1.15. These are the decimal equivalents to the percentages. This is the reason why we do 1 times by 1.13 for the tax. We're actually talking about 113%. The 100% number is the number that you start with, and then you grow or decay from there depending on what you're doing. And so you can interpret questions as growth or decay versus whether or not they're 1 or above or below 1 for decay. Above 1 for growth and below 1 for decay. So here's a question. This is saying that Starbucks stores are increasing approximately 20% per year since 2003. If Starbucks continues to expand at this rate, how many Starbucks stores would there be in 2025? We're going to use an equation. First, I want to just talk through, because we're not always given this 20% number if you're given a table of values like this. So I want to talk about where does that 20% number show up in the table of values. And it comes back to that common ratio. If we divide the successive values, we actually get a bunch of different numbers, and they're all around 1.2. 1.2 is actually what we're multiplying by each time. And the 1.2 means that we have 100% and we're growing by 20%. 1.2 is 120%, a 20% increase. This is not the official way to get the 1.2. If we actually want to do this officially, we would actually divide 15,011 by 7,225 and then take the fourth root. And that's how you actually get exactly what you're growing by every time. If you want to summarize it, I'm okay if you take the average of these four numbers, but the official way to do it is to take the fourth root of the 4. But for our purposes, we're really just going to look at these, and it's really a scatter plot anyway. And so we're just really going to look at these 4 numbers and say it's around 20%. Now this one's 19, this one's 19.5, this one's 21.5, this is 20.7. So we'll say around 20%. For accuracy, though, instead of starting with 7,225, because 7,225, these numbers have already happened, we're actually going to start with the 15,000 number. And we're going to multiply by 1.2 the number of years left till 2025. So we're going to do this for 18 more years. If we multiply 1.2 out 18 more times, we use an exponent for that, and we get an answer of 399,643. Be curious to see what happened and how many Starbucks there actually are in the year, say, 2015. The next question is a depreciation question. So a new car costs $24,000 and it loses 18% of its value each year after it's purchased. We, of course, know that cars will depreciate faster at the beginning, and that actually fits with an exponential decay type question. You'll lose the most of your amount lose the biggest amount at the beginning, and you lose a little bit less as you go on. Determine an equation that would represent the amount of money the car is worth after X years. So the question is, what percentage do you have left? Because that's what we multiply by every time. So we start with our value of 24,000, and to create the equation, we're just going to multiply by 0.82, which is the 82% left. And we're going to do that a whole bunch of times. We don't know how many times. It's a little misleading writing it this way because it does kind of assume that we have to do this a whole number of years. But you can actually do this a decimal number of years as well. And that's what the question is going to ask, is 30 months. We simplify this down to 24,000 times 0.82 to the x. Again, it's 0.82 because 82% is what you're left with. If you started with $100 and you multiply by 0.82, then you'd have $82. And that kind of makes sense that we lost 18%. But if you multiply by 0.18, you're actually losing 82%. Your number's going to be a lot smaller than you would expect. Right? You're going to decay way faster. And we don't want to get that wrong. Like, we want to make sure that we understand, why is it 82%? It's the change from 100. You've gone down 18% from 100. To answer the second question, we got to talk about 30 months, but the question is in years. So we have to convert 30 months to years. A lot of you guys can do that just by thinking about it if there's 12 months in a year. But if we take the 30 and divide it by 12, we get 2.5 years. If we plug 2.5 in to the function for x, then we end up getting $14,613.22. So after 2.5 years, the car is worth $14,000. That seems reasonable. It is going to be certainly less than it was, and it's going to have this exponential decay. Next question is half-life. Half-life in itself is not too complicated. There's going to be something in this question that I really want to talk about. Radioactive isotope has a half-life of 10 days. The half-life means is we multiply by 0.5 each time. And how many times do we do it? Like, we do it every 10 days. We want to multiply by 0.5. So the reason why I kind of talked about a horizontal stretch here is because in the base graph of 0.5 or 1/2 or any base graph too, they go up by 1 every time. If we go up by 1 every time, we actually would multiply by 0.5 every day. We don't want to do that. We want to multiply less often than that. So we stretch it out horizontally from really a scale of 1 to a scale of 10. And so the way we do that is the same way we write an equation for a horizontal stretch. There's 250 grams of the isotope in the chemistry lab. That's their starting amount. So what you're looking for in these questions is a starting amount, what you're multiplying by every time, and then potentially in the second part of the question, what you actually need to sub in or solve for. So we're going to start with 250, and we're multiplying by 0.5 every 10 days. And the way we do that, if we want to let x represent the number of days, is we have to incorporate that horizontal stretch. The horizontal stretch is to do 1/10 in the exponent, or take x divided by 10. You don't have to do it this way, but you'll see in the next question, like, we actually want to model this. So we want to see what this means. So you can describe it. But to solve the next question, as long as you understand that you're going to take the 30 days and divide it by 10, you're going to get that idea, and you're going to only multiply the 0.5 3 times. We don't want to do it 30 times. It's a half-life of 10 days. So you always want to be thinking about what's going on in the question. So 3 half-lives in 30 days. And so the answer is 31.25 grams. How much will be left in a year? A year is 365 days. We have to realize that, because we can't sub in 1, because we've got to do everything in days. So if you sub in 365, we get an exponent of 36.5. Again, you could have done that without writing the exponent this way, just as x is the number of half-lives. So we've got 36.5 as our number. And when we do that in our calculator, we got to realize what's happening. You might see this in your calculator. It depends on your calculator. You might see E. You might see just a blank. This -9 will certainly be in there somewhere. And so now some of your calculators might just give you all these decimals, but you have to understand what this means. And this is scientific notation. We have a little bit more knowledge of this now that we've done negative exponents. And what this is basically doing is, remember how a negative exponent would slide down? And so we're essentially dividing by 10 9 times. And so we take our decimal from where it is, slide it to the left 9 times, and we end up with it here. Very little left, but there is something left. It actually does have value, because we were talking about a lot near somebody's house and saying, oh, it had radioactive material on it, so they have to go through this whole big process to dig it out. So even though the radioactive material is very small now, because it's died off with the half-life, it's still there, and it could still be harmful. In summary, as long as there's no horizontal asymptote change, we actually have a growth and decay problem. And a lot of our problems will be like that. It is probably going to be obvious when there is a horizontal asymptote change. And so we can use this equation just AB to the x, where, as I said, x has to represent the number of times you multiply by b. And so that might not always take the form x. It could be x over 10. But if you want to do it as x, you just have to remember that that's how many times you're going to multiply by b. This is why I kind of wanted to talk about it. We're going to see it again here. A cup of coffee is poured out and left on a table. It's a really neat problem because it's really easy to visualize. Temperature cools according to the formula 70 1/3 x over 20 plus 20. X is the number of minutes, and T is the temperature in Celsius. Discuss each part of the equation, what it tells you. So first off, 70 is the number of degrees above the room temperature at the start. It's a vertical stretch factor. And so we kind of already talked about the 20. 70 is the number that you're above that room temperature. T of 0 equals 7. If you plug in 0, you have an exponent of 0 here. 0 divided by 20 is 0. 1/3 to the 0 is 1. So you have 70 plus 20, which is 90 is the initial temperature. 1/3, watch out for this, because it doesn't mean you're decaying by 1/3. It's not the whole thing that decays. It's just the 70 degrees. So the temperature above the room temperature decreases by 2/3 every time. Or you have 1/3 left every time. The x over 20 means you have a horizontal stretch by 20. So every 20 minutes, the temperature above decreases by 2/3. So the temperature above the room temp of 20 decreases by 2/3. The plus 20 represents the room temperature, and it's what the temperature is going to approach. So you can see that if you leave out the coffee, it's not going to freeze. It's going to approach the room temperature. So it's going to get cooler, but it will only get cooler to a certain point. That's where you get that exponential decay. Temperature after 45 minutes, if we plug in 45, you got to be comfortable plugging that in. So make sure you know you can plug that in and you're comfortable with that. Plug in 45 into your calculator, you should get 25.91. What you can do is do 1/3, use brackets in your calculator. You can do 1/3 to the exponent, 25.91 over 20. You can do 25.91 over 20, write the decimal out for that, do 1/3 to that exponent, multiply by 70. Calculators do have memory functions where you can store things. You really just have to get to know your calculator. And when will the temperature approach 40 degrees? And this is a little bit harder question. Remember that T is the temperature. And so if we want to actually find out when is the temperature going to approach 40 degrees, we've got to plug 40 into the left side. This is going to require us solving for x. And so we've actually never done that before, where we solve for an exponent. And so to do that, kind of like we do in vertex form, we got to get rid of everything to the other side and solve for just this part. So we'll subtract 20 on both sides, divide both sides by 70, and we get 0.2857 equals 0.3333, and use as many 3's as you can, to the x over 20. This question, you really have to ask yourself, what exponent on 0.333 will give you 0.2857? And really, the only way we can do that right now, before you learn the method in advanced functions, is to do guess and check. I just keep going until to the nearest two decimal places. With a base of 0.33, just keep plugging in exponents. Don't worry about the x over 20 right now. Just keep plugging in exponents until you get 0.2857. So depending on your calculator, it could be easier or harder to do that. And so you want to, if your calculator has any kind of memory line display, then you could always just go up and change the decimal. And then we actually narrow it down to 1.14. So 0.333 to the exponent 1.14 gives me 0.2857. So that means that x over 20 has to be 1.14. And if we multiply both sides by 20, we get 22.8 minutes. Okay. This question is probably more challenging in something like this, especially where you have an exponent with a horizontal stretch factor in it. But you could also likely just see this question with an exponent just of an x, or a number not like 0.33, just like 2 to the x equals something. Then it gets a little bit easier to deal with. Okay, but if you can follow through this example and get that 1.14, then you're doing okay. This is probably the most challenging one we'd see. So practice, again, I tried to narrow it down. There's 5 questions on each learning target. I tried to separate them. 15 I leave as a challenge question. So without looking at 15, there's 10 questions to practice. It's really important that you do get practice with this stuff. And I do want to see you making equations with different situations. Okay.